You know that feeling when you're staring at a problem that's so huge, so complicated, you don't even know where to start? Well, it turns out computer science has this surprisingly simple and, well, elegant secret for dealing with exactly that. Today, we're going to unpack a super powerful strategy called divide and conquer. So let's just jump right in. Think about it for a second. How on earth does a search engine sift through billions of web pages in less than a second? Or how does a giant data center sort just unimaginable amounts of information? How do these systems tackle problems that are just that big? Well, here's the secret. They don't. They don't solve the one massive problem head on. Instead, they kind of cheat. They take that one impossible task, they shatter it into millions of tiny, easy-to-solve little problems, they solve each of those, and then they cleverly stitch all the answers back together. That right there is the heart of divide and conquer. So here's how we're going to break it down. First, we'll look at the master recipe for this whole strategy. Then we'll see it in action with searching, finding extremes, and a couple of classic sorting methods. And finally, we'll wrap it all up by talking about why this idea is just so incredibly powerful. Okay, so what is this master recipe? Let's get into the formal definition and the simple, repeatable steps that make this whole thing tick. At its core, the divide and conquer algorithm is pretty much exactly what it sounds like. You take a big problem, you break it into smaller, more bite-sized sub-problems. But here's the really important part. Those sub-problems have to be independent from each other. That means you can solve one without messing up the others, which is absolutely crucial for being efficient. You solve each little piece, and then you merge their solutions to solve the original big puzzle. And this whole brilliant strategy really just boils down to 3 simple steps. First, you divide the problem. You just keep breaking it down until you can't break it down any further. Second, you conquer each tiny piece. You solve it. And third, you merge or combine those little solutions back together to get your final answer. Divide, conquer, combine. Let's see how this actually works. All right. Our first and maybe most intuitive example is something called binary search. It is the perfect illustration of this 3-step recipe for finding something incredibly fast. Now, there is one non-negotiable rule for binary search. Your list of things, your array, it has to be sorted first. But once it is, the logic is beautiful. You just check the element smack dab in the middle. Is that what you're looking for? No? Okay. Is your target bigger or smaller? And based on that one question, you get to throw away half the list and just do it again. Let's actually walk through this. So we're looking for the number 11. Our first middle element is 10. Okay, 11 is bigger than 10, so we can instantly ignore the entire left half of the array. Boom, that's our divide step. In the half that's left, the middle is 22. Our target, 11, is smaller, so we throw away the right half. By just chopping the problem in half over and over, we find what we're looking for like a heat-seeking missile. So it all comes down to this really simple, repeatable loop. You set your boundaries, you find the middle, and you make a choice. Is it the target? Awesome, you're done. Is the target smaller? Search left. Bigger? Search right. You just keep doing that, and this is why it's so mind-blowingly efficient. Instead of checking a million items one by one, you might only have to check, 20 times. It is a staggering difference in speed. Okay, so that's searching, but what about a totally different kind of problem? Let's see how our divide, conquer, combine recipe works for something like finding the smallest and largest numbers in a big list. Would you look at that? It's the exact same pattern. First, you divide. You split the list right down the middle. Then, you conquer each half by finding the minimum and maximum value inside of it. Finally, you combine the results. You just compare the minimum from the left half with the minimum from the right half to find the overall min, and you do the same exact thing for the max. It's simple, it's elegant, and it just works. All right, let's take this strategy and apply it to one of the most fundamental jobs in all of computing, sorting. We're going to look at 2 really famous algorithms, merge sort and quick sort. They both use divide and conquer, but they do it in slightly different ways. So here's where their strategies split. Merge sort's divide step is, well, it's pretty simple. It just keeps chopping the list in half and half again until every single element is in its own little list. Quick sort, on the other hand, is a little more clever about it. It picks one element to be a pivot, sort of a reference point. Then it rearranges the whole list into 2 piles, everything smaller than the pivot and everything larger. The real beauty of merge sort is its foundation. Think about it. An array with just one element is, by definition, already sorted, right? So the divide and conquer steps are almost nothing. The real work, the magic, happens in that combine step, where it carefully merges these tiny sorted lists back together into bigger sorted lists. And this picture just lays it out perfectly. See how the main array at the top gets broken down, 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 until you just have individual numbers? That's the divide phase. Now look at the green boxes. It starts merging them back together, two at a time, making sure each new little list is sorted, until it builds its way all the way back up to that one single, perfectly sorted array at the bottom. Now let's switch over to Quicksort. Its entire strategy, everything, hinges on that pivot. The whole goal is to pick a pivot and then, in one single pass, shove everything smaller than it to its left and everything larger to its right. After that one step, that pivot element is already in its final, correct, sorted position. So let's trace this one. The pivot they chose here is 13, the last element. After that partitioning step happens, you can see the result. All the numbers less than or equal to 13 are on the left side, and all the numbers greater than 13 are on the right. And look, 13 itself is now perfectly placed. It never has to move again. Now, the algorithm just does the same exact thing on those two smaller chunks on either side. So, we've gone through searching and sorting, but let's just zoom out for a second. Why is this one idea, divide and conquer, so fundamental? Why is it so powerful in computer science and really beyond? It really comes down to these core ideas. It gives us a blueprint, a plan of attack for breaking down these scary, overwhelming problems into pieces we can actually wrap our heads around. And because you solve the smaller pieces independently, you can often throw multiple computer cores at them at the exact same time. That's parallel processing, and it's what lets modern systems solve gigantic problems so quickly. And finally, the solutions are combined back together efficiently and, honestly, quite elegantly. You know, this quote really just nails it. It is a clear, repeatable process. Break it down, solve the pieces, and put them back together. This isn't just some computer algorithm. It's a powerful way to think about solving almost any problem. And that kind of brings us to our final thought. This recipe, it doesn't just apply to sorting numbers on a computer. Think about planning a huge project, or writing a book, or even just cleaning your entire house. Now that you know the recipe, what big problems in your life could you start to divide and conquer?